Welcome viewers to the last segment of the 9th lecture of the course of Introduction to Category Theory. So in the last segment we were with the proof of proposition 1 and we verified the first condition to be satisfied called the identity law for the functor definition, and we saw that it holds. In fact, you see that we replaced this calligraphic X with calligraphic Y in this diagram with the underlying text to be the same for these two pre-orders, and we replaced this function which is actually a function between the vertices of the associated with the associated graphs, and we saw that, and we also saw that here, in order for this diagram to commute, you must have this map to be an identity map between these two sets, R sub calligraphic X to R sub calligraphic X. So what does it mean? It means that you have the between the set of vertices you have the identity map, and between the set of arrows you also have the identity map, meaning that nothing is changing, meaning that it is precisely the identity map between these two graphs, from the graph to itself, okay? Because they are the same graph, okay? That's what's written here, okay? So now we need to verify the preservation. So this was the preservation of the identity. Now we need to verify the preservation of composition for the definition of functor. Let's do it. Okay. So that way we will be able to prove that the functor from the category of pre-orders to the category of graphs is indeed a functor. Okay? All right. Now, see that F is taken to be the following pre-order morphisms, and G is another pre-order morphism from Y to Z with calligraphic X being the pre-order given by this pair, and calligraphic Y is the pair, and calligraphic Z is the pair. These are three pre-orders, okay? And these are the two pre-order morphisms. And here, for this case, the relation is given by the subset of the Cartesian product of X with itself So in this case, R sub y is a subset of y Cartesian product with itself, and R sub z is a subset of z cross z. Okay? These are the things given. Now we have, so using the same diagram that we were discussing earlier, we see that this is the commutative diagram. Okay? This is the usual inclusion map. It's a subset of X cross S, so there is an obvious inclusion map. And then we showed earlier that there exists a unique map from Rx to Ry so that this diagram can use. And this is Y cross Y, and this map is simply F cross F, and we call this unique map to be H. Alright. This can use. Alright. And now, since G is another pre-order morphism from Y to Z, okay, then we have this part of the diagram, Ry to Rz, which we call H prime, and then from Rz to Z cross Z. And this map is G cross G, and this diagram also continues. Okay? And what is this map? This map is going to be H prime composed with H, and this map is going to be G cross G composed with F cross F. And check that this is indeed G composed with F cross G composed with F. Like, you know. So you are going from X to Z via G composed with F, and from this X to this Z via G composed with F. Okay. So they are the same. Alright. Good. So what does that mean? It means that we have this commutative diagram from Rx to X cross S via the canonical inclusion map. And here we have our Z, and there is another inclusion here which we call I Z, and this is Z cross Z, and this map is nothing but G composed with F cross G composed with F, right? And this map is H prime composed with H. Okay, and this diagram continues. Okay, so this is what we get from here by taking the commuting rectangle. All right. So the commuting rectangle is given by this single commutative diagram. Okay, so what have we seen? We have seen that, therefore, it means that the composition is preserved under this functor. So we have seen that PG composed with PF. So, in fact, we can see it from here because I know on the left you have a see that this is a graph homomorphism on the left, and on the right you have another graph homomorphism. And we need to show that. So we need to show that these two graph homomorphisms agree with each other. So when this happens, it means that they agree with each other on both the vertices level and the arrow levels. Okay, so which means that it will only hold if we have PG composed with F. It's zero component, meaning that the vertex is the function associated with the vertex. Okay, it takes the vertices to from one graph to the vertices of another graph. Okay, and the zero component of the right-hand graph homomorphism is this. Okay. And the arrow level, it tells you that PG composed with F. This component should be equal to the arrow component of the right-hand side. Okay. So this guy is equivalent to this fact. These two facts. Okay. And we can easily see that this holds using this commutative diagram. Let's see how it happens. Okay. This was that this guy was defined as, so when we were dealing with when we studied the category of graphs, we explained that this is nothing, this was defined as PG 0 composed with PF 0. And what is this? What is the vertex component of this graph homomorphism? Okay, is simply G. Okay, so G takes the set Y to the set Z, and Y was the set of vertices, right? So there was an associated graph here, which we denoted by, remember, Y was the set of vertices, and RY was the set of arrows, and SRCY and SRCZ. This was the corresponding graph. Okay, so G is the map that takes Y to Z, and here as well, the graph associated with the pre-ordered Z was found to be Z is the underlying set, which is the set of vertices, and R subcalligraphic Z, and S or C sub Z, and TGT. Sorry, this is not S or C. This is TGT. TGT sub Y. Okay? And this is S or C Z. This is TGT sub Z. So, this is the graph associated with the pre-order Y under the functor P, and this is the graph associated with the pre-order calligraphic Z under the functor P. And talking about this map G, which takes the set of vertices of this graph to the set of vertices of this graph. Okay? And that is precisely the zero complement, okay, and which is simply G, and the zero complement here of this graph homomorphism. Okay, so we simply denote this. So to be more precise, this was the pre-order, and G was the map from pre-order, this graph to that graph. Okay, so the zero complement of this is simply G that we have seen here, because G is the map from Y. So is F here? F is the zero complement of this graph homomorphism. Similarly, we can check that. So now here, for this case, it is supposed to be PG1 according to the definition that we provided in the segment where we describe graph homomorphism. Then it is supposed to be so now the arrow thing, okay? The arrow. So the arrow was for the first one. For this is the arrow. Okay, this is the set of arrows here are Y, the set of arrows are Z, and the set of arrows are X. So this is the map PG1, and this is the map PF1. Okay. Now, from this picture, we see that G composed with F, this is the graph homomorphism. Okay? This is the picture of this. This is the commutative diagram associated with this graph homomorphism, this commuting rectangle. And what is at the vertex level, this is simply G composed with F. Okay? G composed with F. Since this is the map, G composed with F is a map between the corresponding sets of vertices from X to Z, and the map between the sets of arrows are X to R Z, which is denoted by PG circle F sub 1 to be H prime composed with H. Okay? So this is also H prime composed with H. So we have found that, let me erase, I need some room here. So we have checked that P G circle F sub 1 is equal to this guy, right? Is P, G, circle P, F sub 1. And we have shown that this is also G composed with F, and this is also G composed with F. Okay? And we also have shown that on the vertex level, right, we have P, G, circle P, F sub 0. So what does it mean? The two graph homomorphisms agree with each other, meaning that at the graph homomorphism level, they should agree also. P, G composed with F is exactly P, G, circle P, F. This way we prove that the composition of morphisms is also preserved under this functor P. Okay? This way we check that P from the category of preorders to the category of graph is indeed a functor. Okay? Good. Now we move to the discussion on natural transformations. Okay? So natural transformations. Let me give you the definition first. Natural transformations. Natural transformations. Definition. Natural transformation okay. Let me change my marker. Let calligraphic C and D, calligraphic D, be categories, okay, and let F from this calligraphic C to calligraphic D be a functor, okay? Be a functor. These are the given information. Natural transformation alpha. Sorry, we need two functors, okay? One is this one. So we need two functors. Let F and G be functors. Okay? So what do we have? We have two given categories and two functors between the same two categories. Okay. So f is a functor from C to D, and G is also a functor from C to D. Now, there is a transformation, or what we call a natural transformation between these two functors. Okay? So, a sort of a map between one functor to another functor, from F to G. That we are calling a natural transformation. A natural transformation alpha from F to G denoted by alpha from F to G is defined as follows. So we are defining natural transformation. One announces, so like before, like we did in the case of the definition of category, like we did in the definition of functor, we also have a bunch of constituents conforming to some law that we need to mention. So one announces some constituents, one announces some constituents. Where are the constituents? A, components. So there is just one type of constituents here, which are just components, and asserts that they conform to some laws, that they conform to some laws that we are going to call naturality squares. Naturality squares. So these are some just commutative squares, okay? Naturality squares. So specifically one announces A for each object. So for each object C in the set of all calligraphic C. Okay. A morphism, so for each object small c in this in all calligraphic C in this set, so which means that for each object C in this category C, there should be a morphism alpha C from, I need to check if it's the video is still running. Yeah, it's still running. That's good. So from there is a morphism between these two objects in the category D. So FC is an object in the category D, and and GC is another object in the category D, okay? Because G is a functor from C to D. So is F from C to D. So these are two objects in the category D, and alpha C is taken to be a morphism in the category D. So these are all happening in the category D. And that's what we are writing now in the category D. And this alpha C is called the C component of alpha of the natural transformation, okay? Of the underlying natural transformation. This is called the C component of alpha. So for each object C in the category C, a morphism in D is given like that, which is called the C component of alpha. One asserts that the following law holds. The following law holds. 1. For every morphism H from C to C prime in the category C, the following square called the naturality square for H must commute. Let me draw the commutative square now. I'm going to erase this opening part of the definition. So this is the naturality square. So this was the initial map, the morphism between these two objects, okay? H, and associated to each such morphism, you can find a square that I'm going to draw now. So under H, FC is taken to FC prime under this morphism FH. Okay? Because F is a functor, right? Between the categories C and D. And under the functor G, so in this row, GC is going to G C prime with the morphism GH, and from HC to GC is this component, C component of the natural transformation alpha, and this is the C prime component of the natural transformation alpha. Okay? And this has to be. So, okay, let's go over the definition again. For each object in the domain category of the two functors, we must have a morphism in the codomain category of the functor, of the two functors. And these are the constituent parts. I mean that the C component of the natural transformation, this is called the C component of the natural transformation. And under this definition of constituents, we must have a naturality square for each morphism between any two objects in the category C, which is this one. Okay? Remember that a naturality square always holds for any morphism between any two objects in the domain category. Okay? This is the domain category. See that F and G are both functors from the category C to the category D. This is called the domain category, and this is called the domain category. Okay, now it's time to give you examples. So let me give you a very simple examples using graph. Okay, we are all familiar with the notions of graph. We studied every bit of details of graph theory that is required for category theory, for doing category theory in a detailed way. Now we are going to study an example of natural transformation using graphs. Okay. Example. Consider the categories C and D drawn below. So I'm drawing two categories below. So C is this category. There are two vertices in the graph. We denote them by 0 and 1. And there is an arrow in between from one vertex to another vertex. And there are two identity arrows. The first one being ID0 and the second one being ID1. It's easy to check that it indeed forms a category. We have done this type of examples before. Now we have another category. Here, with three vertices, a graph with three vertices. Let us call one of them to be A, another B, and the remaining one as C. And there this maps from A to B, we have an arrow F. From B to C, we have this arrow G. And from A to C, we have the arrow H, which is nothing but decomposed And there are three loops, ID A, then this is ID B, and this is ID C. Okay, this is, so we have checked earlier that this is indeed a category. So these are the two categories. Now consider the functors F and G between these two categories. Okay. C is the same as 1 and D is the same as 2. Okay. Where, so we are defining them as follows, where f of 0, so 0 is an object, so these vertices are objects and arrows are morphisms between objects, okay, for this category C. And so same holds for the category D, meaning that A, B, C are objects of the category D, and the corresponding the arrows are the morphisms between objects of this category D. So so F is a functor from 1 to 2, and F is supposed to take objects to objects and arrows to arrows. So F0 is supposed to be an object in this category D, and this is defined as A, this object. And F1 is equal to B, G0 is equal to A, G1 is equal to C. Okay? Now I give a very simple exercise to you to check that. F and G are indeed functors from 1 to 2. This is something for you to check. Okay? Using definition. You should be able to check. So it turns out that there is only one natural transformation in this case, okay? And which is what? Which we denote by alpha. We denote the natural transformation here by alpha, which is what? So in order to completely describe alpha, we have to first identify its components, okay? And see that there are two objects only in the domain category, meaning that object of C is this two element set 0, 1. So there will be two components of alpha, namely alpha 0 and alpha 1. Okay? See that? So there are two components of this natural transformation. In fact, so how did we define alpha C? So you see that alpha C is a map from FC to GC, okay? So what is alpha 0 then? Alpha 0 is a map from F0 to G0, right? And alpha 1 is a map from F1 to G1. Alright, since F0 is A and G0 is also A, so alpha 0, well, let's call it alpha 0, so I think I should call it alpha sub 0 instead of alpha of 0, and here alpha sub 1 instead of alpha of 1. These are the two components of the underlying natural transformation. So this alpha sub 0 is nothing but the identity map on vertex A in the category D. Okay? And alpha 1, so since F1 is B and G1 is C, in the category D, the morphism between B and C is G, so alpha 1 is nothing but G, which is a morphism between B and C in the domain category D. Okay? Alright, now we already have seen in the definition of natural transformation that associated to each morphism in this domain category, we can find a naturality square. So if we choose the morphism to be this one, so okay, so I want to create room for myself. What should I erase? I need this information. I need these two diagrams, so I can erase this. Okay. So, let me erase this part, okay? Create a little bit of room here for myself. So now I'm supposed to draw naturality squares associated with one of the morphisms in this category. Let's take the morphism P from 0 to 1. Okay? The naturality square associated with this morphism in category C well, this is the general type of naturality square. So in our case, so it's going to be F0 to F1 under the action. So the morphism is going to be FP. Okay. And then you have G0. The functor G is acting on this morphism. G1 and GP. and this is the zero complement, the zero complement of the naturality transformation, and this is the one component of the naturality transformation. Okay. And this guy is equivalent to what is f of 0? F of 0 is A, and f of 1 is B, okay, and g of 0 is A here, and g of 1 is C, okay, and what is FP? FP then. FP is a morphism in the category D, and what is the morphism between A and B in the category D is F. So this guy is F. Alright. Now GP is the morphism between G0 and G1 in the category D. So in other words, we have to take the morphism between A and C in the category D. What is the morphism between A and C in category D? G composed with F. Okay. And alpha 1, we have already seen that is G, which is the morphism between B and C in the category D. And this, we have seen that this is just the identity morphism on the vertex A in the category D. Okay? So this is how, so it's easy to see that this diagram commutes. So we have found the naturality square associated with this map. Okay, this diagram commutes since you see that you can go from A to C using this path or that path, and they should produce the same result by seeing that G composed with F is the same as G composed with F composed with IDA. Which is trivial to see. Okay. This diagram commutes. So since this diagram commutes, this is the naturality square associated with this morphism P from 0 to 1 in the category C. Okay. Now you may ask, what happens with the other morphism in the category C? Let's choose another morphism. Let's choose the morphism ID1 from 1 to itself. Okay? This morphism I'm choosing from the domain category. And what will be the naturality square associated with that morphism? That naturality square should also be a commutative diagram. Okay? So that the underlying transformation is a natural transformation. Okay? So let's see if that's a commutative diagram. So in this case, we have f of 1 is mapped to f of 1 by a morphism f of ID1, okay, and g of 1 gets mapped to g of 1, right, by a g of ID1, and there is this one component of the natural transformation alpha, and again the one component of the natural transformation alpha. Okay. Alright. Now, it is important to see that f and g are both functors. Okay. So they should preserve the underlying identity morphisms according to the definition of functors. So which should be the same as ID of F1, which is the same as ID of, what is F of 1? B. The identity morphism on B. Okay? And it should be ID of G of 1, right? Under the preservation of the identity morphism, according to the definition of functor, and this is going to be ID of, what is G of 1? Is C. Okay? So this diagram is equivalent to the diagram that I am going to draw now. F of 1 is B, right? And it's a map from B to itself. And F of ID1, I have just shown that using the definition of functor, is IDB. And now, what is G of 1? G of 1 is C. G of 1 is C. And this G of ID1 is IDC. Okay? And from B to C, you have this one component of the natural transformation, which is G, and this is the same as the one component of the natural transformation, which is again G. Now, it is easy to check that this diagram proves. Okay? Since G composed with IDB is this fact, okay? Is the same as IDC composed with G. It is easy to check that this holds, and therefore this diagram also concludes. So it amounts to the fact that this diagram, this commutative diagram, is the naturality square associated with this morphism in the domain category C. Okay? And this commutative diagram is the naturality square associated with this morphism in the domain category C. Okay? Similarly, you can check that you can find the naturality square associated with this morphism 0 to itself, which is the identity morphism on 0. Associated with that morphism, you can find a naturality square, a commutative diagram. One should be able to see that immediately. Okay? So I leave it as an exercise. So in the final part of this last segment, we are going to discuss graph homomorphism and natural transformations. Okay? Let me see if the video is still going. Yeah, still going. So let me erase everything. We are done with the first example of natural transformation. Now, we're going to go see a second example of natural transformations in terms of graph homomorphism. In other words, we will see that graph homomorphism can be interpreted as a natural transformation between functors, where graphs are precisely functors. Okay? Let's do it. Graph homomorphism. Morphism and natural transformations. Okay, so now we write a graph can be considered as a function, functor. Graph can be considered as a functor. How does it work? Let us discuss first, okay? In the following way. In the following way. Consider the category depicted below. Consider the category depicted below so I'm gonna write this, denote this category with GRIN, abbreviating graph indexing category. Okay, this category will be called graph indexing category, and it looks like a graph with 2 vertices and 4 arrows. So the vertices are labeled as AR, BE, there are 2 loops or identity morphisms called IAR and IVE, and there are 2 parallel arrows called SRC and PGT. So it can be easily seen that it is a category. Okay. So now then it's a category, and then a functor G from this graph indexing category to the category of steps. What is this? What is this? What is this functor? Is the same thing as two sets GAR, GVE. These are the objects in this category. In other words, they are sets, okay? And there will be 2 maps here under this functor, which are, and 2 functions, GSRC, okay? Right? Between GAR and GBE, GTGT from GAR to GBE. Okay, so you have 2 maps and 2 maps and 2 sets in this category set, the category of sets. This is precisely what is needed. So these are precisely what we need to have a graph, right? So the set of arrows, the set of vertices, and the source function and the target functions. Okay? So the quadruple GVE, GAR, GSRC, and GPGT, this quadruple is the underlying set, or that we can call a graph. Okay? Is indeed a graph. So we call this category the graph indexing category. Okay? Let me write it. We don't have much time to write everything in detail. They can be found in the lecture notes. Graph indexing category. Okay? Correct. So now, these are two functors, G and G prime, can we find a natural transformation between them? That's the question. So let's erase these things. Okay. Okay. A natural transformation, a natural transpose of two such functors, So we have seen that G and G prime, they are functors from the graph indexing category to the category of sets. Now we have chosen two such functors and we're trying to find the natural transformation between these two functors. And that involves, so this, if this is the natural transformation, then this should involve two components, right? Should involve two components, namely alpha AR, alpha sub AR, and alpha sub BE. Okay? There will be two components associated with these natural transformations because there are two objects in this category G, which are AR and B. That is, object, well, so let me denote these things very clearly. These are functors from the category of GRIKN to SET, okay? So we are choosing not from here. This is the category, right? And right, yeah, from here. So we are choosing, right? Sorry. So we are choosing object from this domain category. Okay. And this set of objects of the domain category is precisely a two-element set, AR, BE. Okay. So given by, so there are two components of the natural transformation. Okay. A alpha sub AR is isomorphism. Okay. Here is isomorphism. Amorphism here is a function. So it's a function between GAR to G A R prime. Sorry, G prime A R. Okay. And alpha sub D E is a function from G V E, this set here, to G prime V E, this set here. Okay. Good. So there should be a naturality square for each morphism in this domain category. Okay. So let us take that morphism to be S or C from AR to V. You could have chosen some other morphism as well. You could have chosen PGT or the identity morphisms, but we're choosing S or C, okay? And we can also choose the morphism PGT from AR to BE as well. Okay? So these are two morphisms in this domain category, graph indexing category, and we are going to construct the two naturality squares associated with these two morphisms in the domain category. What are those? So associated with this map, we have this naturality square from GAR to GDE. There is a map between these two sets in the category of sets, which is called GS or C, which is the source function. And then we have for the other functor G prime VE, and this is G prime SFC, and there is these two components of the natural transformation, alpha AR, alpha sub AR, and alpha sub DE. Okay? And there is a naturality square associated with this morphism in this graph indexing category, which is G AR to G VE, and this is G PGT. This is the function between these two sets. So is this mu, the other function here between these two sets, G prime AR to G prime VE, and the function is G prime PGT. Okay? And now here are the two components of the natural transformation, which is alpha AR, and this is alpha V. Commutative diagram. Okay. Now, the important thing to note is that it can be interpreted as a graph homomorphism. Let's see how. Let me erase. So I want to keep these two diagrams. Do I need it anymore? No, I don't need it. Okay, so think of these two commutative diagrams as a graph homomorphism. has a graph homomorphism G of VE is a set of vertices. G of AR is a set of arrows, and the source map and the target maps are G of SRC and G of TGT. So this is one graph. And what is the other graph? G prime of VE. There is another quadrature here. Then G prime of AR is a set of arrows in the second graph, and G prime of SRC is the source map in the second graph, and G prime of TGT is a target map in the second graph. Okay? So now I want you to compare these two diagrams. Compare the two diagrams below. By below I mean this one, with the graph homomorphism. DA SRC TGT to B prime A prime SRC prime TGT prime. Okay. In terms of the component functions, in terms of the component functions, there were two component functions, one at the vertex level, the other one at the arrow level. Were those? One from A to A prime was F1, and another one from B to B prime was F0, and there was a source map from A to B. There was another source map from A prime to B prime, and at the target level we had another map from A to A prime, which is F1 again, and from B to B prime is F0, and there is target map from A to B and target map from A prime to B prime. And these two diagrams complete. Okay? So, here this with that. Okay? Just rotate it to match this one with this one, and rotate it clockwise 90 degrees to compare this one with that one. Not clockwise, probably anti-clockwise. This one. Compare this one with this one. Okay? So GTGT is analogous to TGT. TGT prime is analogous to G prime TGT. And F1 is the function between arrows. And function, this is a set of arrows, this is a set of arrows. So this F1 is synonymous to alpha AR, and F0 is synonymous to alpha VE, and for the other diagram as well. So this is the counterpart. This is the counterpart of this diagram, and this is the counterpart of this diagram. Okay. So in particular, so we have seen that in particular, the components of natural transformations, the components, what are the components? Alpha AR and alpha BE, right? These are the components of the natural transformation alpha are acting like the components. What are the components? Let me write the components in proper order. Alpha VE and alpha AR. Okay? And the components are F0 and F1. The components of the graph homomorphism Okay. So alpha VE, this component of the natural transformation, is acting like the component function between the set of vertices. And alpha AR, the AR component of the natural transformation, alpha is acting like the function between the sets of arrows, okay, of the two graphs. Alright, this is pretty much it. Now we see that how we can think of graph homomorphism as a natural transformation between two functors, which are nothing but graphs. Okay? So this ends our 9th lecture here. So in this lecture, we gave the definition of categories, and following which we considered three very important examples of categories: the category of graphs, the category of monoids, and the category of preorders. Okay? Then we took an example of something which is not a category, and eventually modifying the constituents of the underlying structure, we turned it into a category. Alright? Then we gave the definition of a functor and considered a couple of examples of functor. Then we gave the definition of natural transformations between functors, and we also considered a couple of examples. Alright, so that ends our course of Introduction to Category Theory. We did not find time to study the finite limits and limits in the abstract categorical setup. So I will try to provide a couple of lecture notes in docs. So if you are interested, you can have a look at them. Thank you very much.